about solubility rules. So what are solubility rules? Well, we understand that not all ionic substances will dissolve. Some ionic substances will dissolve, they're called soluble, because they have a weak attraction between anion and cation. Since there's a weak attraction between the positive and negative in that ionic compound, water is able to separate them. So water is able to pull apart the positive and negative ions. Other ionic compounds have a very strong force of attraction between positive and negative, so water is not able to pull them apart. The solubility rules are a set of rules that we use to figure out whether a substance is going to be soluble or insoluble. If we determine by looking at its formula that it is soluble, then it will dissolve in water. If, according to the solubility rules, it is insoluble, it will not dissolve in water. So, the solubility rules can be found on the back of your periodic table. This is a picture of the back of your periodic table, and it should look pretty familiar. We've used two parts of this reference here before. This center area is the solubility rules. So this is going to be the section that we're going to be using. I have put a copy of the periodic table and formula chart in the class materials folder under files. Some compounds contain ions that are always soluble. So if a compound contains one of these ions that's always soluble, it will dissolve. So these ions include the alkali metals, are always going to be soluble. Ammonium is always going to be soluble. Acetate, nitrate, cyanide, and all of the chlorate ions. So all of these, if they are present in a compound, will lead it to be soluble. So any compound containing an alkali metal, any compound containing an acetate ion is going to dissolve in water. There are some ions that dissolve most of the time, except for a few exceptions. So the halogens, bromine, chlorine, and iodine will dissolve most of the time. When they will not dissolve, when they're insoluble, is when they're bonded to silver, lead, or mercury. So for example, if I have the compound aluminum bromide, it is going to dissolve, it's soluble. However, when bromine is attached to silver, when those two are bonded in silver bromide, that is not going to be soluble, so that's an insoluble compound. Sulfate is another ion that has some exceptions. The exceptions for sulfate are strontium, barium, lead, and mercury. So you can see that some of those are common. So most of the time sulfate will dissolve. However, it will not dissolve when it's bonded to strontium, barium, lead, or mercury. So for example, magnesium sulfate would be a soluble compound, but barium sulfate, because it contains that exception ion, is not. There are some compounds that contain ions that are mostly insoluble. So most of the time, these ions will cause a compound to not dissolve in water. Now, all alkali metals and all ammonium compounds will dissolve. So that rule actually comes first. If it contains ammonium or an alkali metal, it's going to dissolve, period. And so that's why those are exceptions to these. So carbonate, phosphate, chromate, and dichromate. Unless those ions are bonded to ammonium or an alkali metal, it's going to be an insoluble solid compound that does not dissolve in water. However, the only way you can get these guys to dissolve is if you put them together with ammonium or an alkali metal. So for example, iron carbonate would be insoluble. But potassium carbonate is going to dissolve. It's going to be soluble because of the presence of that alkali metal in the compound. Again, there are some more mostly insoluble ions that cause compounds to be insoluble. However, they have more exceptions. So some of the alkaline earth metals can be exceptions here. So calcium, strontium, and barium, in addition to ammonium and the alkali metals, are exceptions for the following ions: hydroxide and sulfide. So, for example, magnesium hydroxide would be considered insoluble. However, calcium hydroxide, because it contains that exception ion, is going to dissolve. So, we've got some practice problems here. Sodium bromide. It's going to be soluble. Bromine is mostly soluble, and sodium is an alkali metal, so that's going to dissolve. Lead bromide. So bromide is a soluble ion, however, lead is one of those exceptions, so this would be insoluble. Silver nitrate. So the nitrate ion is one of those ions that is always soluble, no exceptions. So this is going to be soluble. Iron nitrate. Again, it contains nitrate, so it's going to be soluble. Silver acetate. Again, that acetate ion was on our list of always soluble ions, so that's going to dissolve in water. Silver chloride. Chloride was on that list of soluble ions, however, silver was one of the exceptions, so that is going to be insoluble. Potassium hydroxide. Hydroxide was one of those ions that's going to be insoluble most of the time, but since there's an alkali metal in the formula, it's going to be soluble. Calcium carbonate. So carbonate was on that list of ions that are insoluble unless they're with an alkali metal or ammonium. And calcium is not an alkali metal, so this is going to stay insoluble. Ammonium sulfide. Ammonium was on that list of things along with the alkali metals that's always soluble, so this is going to dissolve. Okay, so what does this have to do with chemical reactions? Well, a lot of ionic compounds form during double replacement reactions. So in a double replacement reaction, you start off with two ionic compounds, and the cations switch places to form new compounds. So here's our example. If I put together sodium bromide and silver nitrate as my reactants, what's going to end up happening is the sodium and the silver are going to switch places, and that's going to create new compounds that are my products. Now, anytime you put together a positive and a negative, you need to make sure that you look at the charges and write a formula that balances charge. In this case, all of my charges canceled out. They were all +1 or -1. Notice, though, that my sodium and silver switched places. So instead of sodium bromide on the product side, I now have sodium nitrate. And instead of silver nitrate on the product side, I have silver bromide. If we examine those products carefully, we'll notice that one of them is soluble, but one of them, according to our solubility rules, is not. It's insoluble. That silver bromide is going to be insoluble because silver is an exception to the solubility of the halogens. So anytime you have an insoluble product, we call that a precipitate. It's going to be the solid that forms during this double replacement reaction. That's why double replacement reactions are called precipitation reactions. The insoluble precipitate is that product that gives this type of reaction its name. So are all double replacement reactions precipitation reactions? No. We know that along with precipitation reactions, acid-base reactions are also double replacement reactions. No solids form during an acid-base reaction. Sometimes those products are soluble, both of them. So in that case, we really say that no reaction occurred because all we did was put some dissolved stuff in water and it stayed dissolved. It's sort of like if you mixed sugar water and salt water. No reaction occurs, everything's just dissolved in water. So how do we determine whether or not a precipitation reaction does cause a solid precipitate to form? Well, the first thing we have to do is we always have to look at the reactants we're given, and we have to finish writing the equation. So remember that your anion and your cation are going to switch places, and make sure that you look at those charges when you write the formulas for the products. So if I look up the charge on ammonium and hydroxide, NH4 has a +1 charge, hydroxide has a -1 charge. Iron, since it's bonded to two nitrates, is going to have a charge of +2, and nitrate, each nitrate ion, has a charge of -1. So when I start putting things together, when I put the iron with a charge of +2 together with the hydroxide that has a charge of -1, those two things don't cancel out, which is why a subscript is going to be necessary to write the formula for iron 2 hydroxide. After you've written the correct formulas based on charge, go back and put coefficients into the equation to make sure that the equation is balanced. After you've written that equation, you then need to examine the products and determine whether or not they're soluble or insoluble. So if I look at those two products, I have ammonium nitrate, which contains 2 soluble ions, so that's definitely going to be soluble, and iron hydroxide, which contains the hydroxide ion, which is mostly insoluble, and iron is not an exception. So iron hydroxide is going to be insoluble. So iron hydroxide would be the precipitate, that solid that I noticed forming in the test tube during this chemical reaction. Once we've written out the equation and determined the solubility of each of the products, we can go through and we can put state symbols next to each chemical formula in that chemical equation to describe it. If that compound is soluble, based on our solubility rules, then we put AQ in parentheses after it. That means that it's dissolved in water. An aqueous solution is one in which water is a solvent. If we determine that the product is a solid, then we put an S in parentheses after its formula. That lets me know that that's in the solid state, that it is not dissolved in water like the other compounds. If I do that for each of the formulas in that chemical equation, I notice that both of my reactants were aqueous. They were soluble in water. My soluble product has AQ after it to indicate that it's dissolved in water. And the iron hydroxide formula has the S after it, indicating that that was the solid precipitate that is not dissolved in the solution, but rather is forming a crystal solid at the bottom of the test tube. I hope that this was helpful and informative. Please make sure to let me know if you guys have any questions.